I'm working with a dataset containing information about customers, including their tenure, how long they've been customers, monthly charges, contract type, like month to month, 1 year, or 2 year, and whether they churned, stopped being a customer. This is typical data for a customer churn prediction problem. Let's build a model to predict churn. The dataset features are tenure, a number representing the customer's length of service, monthly charges, also a number, contract type, a category like month to month, 1 year, 2 year, and churn. A binary variable indicating whether the customer churned, 1 for yes, 0 for no. I need to prepare this data before building my model. I will use standard scaler to scale my numerical features, tenure, and monthly underscore charges. Standard scaler transforms the data to have a mean of 0 and a standard deviation of 1. This helps algorithms like logistic regression perform better and converge faster. I'll use one-hot encoding to handle the categorical feature, contract underscore type. This means that I'll create new binary, 0/1, features for each contract type. For instance, if the contract is month to month, the month to month feature will be 1, and the others will be 0. This converts a categorical feature into a numerical representation that machine learning algorithms can understand. After preparing the data, I'll train a logistic regression model. This is a great choice for binary classification problems like this one, where I'm predicting whether a customer will churn or not. This refers to the dataset after the cleaning and transformations that I will perform, scaling, one-hot encoding. It's the ready-to-use dataset that I will give to the model for training. I recommend one-hot encoding for the contract underscore type feature because it's categorical. This converts the categories into numerical representations that machine learning algorithms can understand. For example, if contract underscore type has values month to month, 1 year, and 2 year, one-hot encoding will create 3 new features, each representing one category. Each data point will have a 1 in the relevant feature and 0 in the others. It's a standard and effective technique for handling categorical data. I suggest scaling tenure and monthly underscore charges using standard scaler. Standard scaler transforms features to have a mean of 0 and a standard deviation of 1. This prevents features with larger values from dominating the model and improves the performance of many machine learning algorithms, like logistic regression. Think of it as leveling the playing field for your features. I don't think label encoding is needed for the churn feature. Since churn is already binary, 0 and 1, logistic regression can handle it directly without further conversion. Label encoding would be redundant and potentially harmful. Let's keep things simple and avoid unnecessary steps. I don't recommend PCA in this case. PCA is helpful for high-dimensional datasets, but we only have a few features. Applying PCA before scaling can lead to suboptimal results because PCA is sensitive to the scale of the features. I suggest that we save PCA for scenarios with many features. Let's not overcomplicate things unless it's truly needed. I'm building a machine learning model to predict which customers will leave, churn. This involves preparing the data properly before I train the model. My data has numbers representing how long a customer has been with this tenure, and how much they pay monthly underscore charges. I also have categories describing the customer's contract type, such as monthly, yearly, etc. I want to predict whether a customer will churn or not. This is a yes, no question, represented as 1, churn, or 0, no churn. To get my data ready, I need to do some pre-processing. Because the contract type is categorical, I need to convert it into numbers. One-hot encoding creates new columns representing each category. For example, if a customer has a monthly contract, the monthly column will be 1, and others will be 0. I'll scale the numerical features, which puts them on a similar scale. Standard scaler makes the features have a mean of 0 and a standard deviation of 1. This helps prevent features with larger values from dominating the model. My target variable, churn, is already binary, 0 or 1. Label encoding isn't necessary here. It's already in a format logistic regression understands. Principal component analysis, PCA, reduces the number of features. I don't need it here because I don't have too many features to start with. Also, PCA usually works best after scaling. After pre-processing, I'll have a dataset ready for my churn prediction model. It will be nicely formatted and ready for training. I'm working with a dataset for predicting customer churn. It has information like how long a customer has been with the company, TENURE, their monthly bill, MONTHLYCHARGES, and their contract type, CONTRACTTYPE. The most important piece of information is whether each customer churned or not, CHURN. This is what I need to predict. Because CONTRACTTYPE is a categorical variable, like month to month, 1 year, etc., I need to change it into numbers a computer understands. One-hot encoding does this by creating new columns for each category. If a customer has a month-to-month contract, only that column gets a 1, otherwise it is 0. This way I don't imply an order where there isn't one. I'm using STANDARDSCALER to make sure that my numerical features, TENURE and MONTHLYCHARGES, are on a similar scale. This helps my model learn better. It does this by making the mean of each feature 0, and the standard deviation 1. This is a good idea. Since CONTRACTTYPE is categorical, I should one-hot encode it before feeding it to the model. This is also a smart move. Scaling TENURE and MONTHLYCHARGES ensures they don't disproportionately influence the model. I don't need this. CHURN is already binary, 0 or 1. So label encoding is extra work that isn't helpful here. PCA is for reducing the number of features, which is unnecessary in this case. I only have a few features, and PCA should usually be done after scaling anyway, so I'm skipping this one. I'm building a machine learning model to predict customer churn. That means I'm trying to figure out which customers are likely to stop using my service. My data includes information about each customer, like how long they've been a customer, tenure, how much they pay each month, monthly charges, and what type of service contract they have, contract type. The most important piece of data is whether or not the customer churned, churn. These are the different characteristics I'm using to predict customer churn. Tenure and monthly charges are numbers, but contract type is a category, like month to month, 1 year, etc. To use contract type in my model, I need to convert it into numbers. One-hot encoding does just that. I create separate columns, one for each contract type. 1 in a column indicates that the customer has that contract type, and a 0 means they don't. This is super helpful for my model. This step is directly related to the previous one. It's what one-hot encoding does. It changes the categorical contract types into numerical data that the model can understand. Standard Scaler is a tool I use to make sure all my numerical features are on a similar scale. This is often very important because features with larger values can dominate the model, even if they aren't the most important factors. Standard Scaler makes them all have a similar average and spread. I use Standard Scaler on tenure and monthly charges. This ensures that these numerical features don't unduly influence my model because of their different scales or units. After I perform one-hot encoding and scaling, my data is ready for the next stage. Now I can use the processed data to train my machine learning model and make predictions. I'm ready to rock and roll. I'm focusing on figuring out the best way to prepare your data before using it to predict customer churn. Think of it like getting your ingredients ready before you start baking a cake. We have information on customers, including how long they've been with us, tenure, how much they pay monthly, monthly charges, and what kind of contract they have, contract type. The main thing we want to predict is whether a customer will leave us, churn. Because contract_type is a text category, like monthly, yearly, I need to convert it into numbers that a computer can understand. One-hot encoding does just that. It creates new columns for each contract type, and puts a 1 if the customer has that type of contract, and a 0 otherwise. I need to put tenure and monthly_charges on a similar scale. Standard Scaler does this by making sure the data has an average of 0 and a standard deviation of 1. This helps my machine learning model work better. This is unnecessary. Churn is already a binary value. 0 for no churn, 1 for churn, so I don't need to change it. Principal Component Analysis, PCA, is a fancy way of reducing the number of features by combining them. But we have few features, so I won't use it here. It's likely to make my model less accurate. After doing steps A and B, my data is now ready to use to train a machine learning model. I'm tackling a problem where I need to prepare data for a machine learning model that predicts customer churn. This involves cleaning and transforming the data to make it suitable for the model. I have a dataset with information about customers, including how long they've been customers, tenure, how much they pay monthly charges, and their contract type. The most important piece of information is whether each customer churned, left the service, or not. To use the contract type information in my model, I need to convert it into numbers. One-hot encoding does this by creating new columns for each contract type and marking them with a 1 or 0, indicating whether the customer has that contract type or not. It's like giving each contract type its own on/off switch. Standard scalar is a method for getting all my features, tenure and monthly charges, onto the same scale. I'll make sure that my model doesn't put more importance on one feature simply because it has larger numbers. Think of it like making sure everyone is measured in the same units, instead of comparing inches to miles. It improves the performance of my model. After I apply one-hot encoding and feature scaling, I have a dataset that's ready for my machine learning model. Now my model can learn efficiently and make accurate predictions.